Today, let's take a look at a common and very important coenzyme for redox reactions, being nicotinamide adenine dinucleotide, or NAD. First is the general redox reaction that occurs. This is a reversible reaction, with the forward reaction shown here being of course the reduction of NAD+ to NADH, and the reverse reaction being the oxidation of NADH back to NAD+. Along with these reactions is a concomitant oxidation or reduction of some substrate, as NAD+ is an oxidizing agent, while NADH is a reducing agent. Due to the ability to transport electrons, NAD+ is commonly known as an electron carrier. More specifically, however, NAD+ is a hydride carrier or a hydride acceptor. You may have heard this term before, so the question becomes, what is a hydride or a hydride ion? As shown, a hydride ion is a negatively charged hydrogen atom. If we look at this in more detail, the hydrogen 1 isotope, also known as protium, meaning it has an atomic mass of 1, is neutral and therefore consists of 1 proton and 1 electron, but no neutrons. This is an important distinction, as any other hydrogen isotope, such as hydrogen 2, which is also known as deuterium, would have 1 or more neutrons in the nucleus in addition to the 1 proton and 1 electron, and therefore would not be the hydrogen seen here. Nonetheless, the protium or hydrogen 1 atom, again, has 1 proton in the nucleus and 1 electron in the valence shell. This provides a balance of the positive and negative charges, providing the atom with an overall charge of 0. By contrast, the hydride ion is a hydrogen 1 atom with an additional electron in the valence shell, creating an imbalance between the positive and negative charge, with the +1 charge conferred by the proton being offset by the 2 -1 charges of the electrons, providing an overall charge equal to -1, making this a hydrogen anion. Therefore, 1 proton and 2 electrons are what is picked up by the NAD+, and this can be carried in the form of NADH. Here's the chemical structure of NAD+. If we look at the name nicotinamide adenine dinucleotide, we can see where this term comes from. On the top here is the nicotinamide, which can be derived from a variety of sources endogenously or from ingestion of vitamin B3 or niacin. On the bottom here we have adenine, which of course is one of the nitrogenous bases found in DNA and RNA. Specifically, adenine is one of the 2 purine bases, the other being guanine. This structure is referred to as a dinucleotide since a nucleotide is essentially a nitrogenous base, a pentose sugar, being either deoxyribose in DNA or ribose in RNA, and a phosphate group. Just as a side note, a nucleoside, by contrast, would be a nitrogenous base linked to a pentose sugar but lacking the phosphate group. However, this structure does contain all 3 components, and in fact it contains 2 of these nucleotides linked by a phosphoanhydride bond. This is where the term dinucleotide stems from. Just as one final aside, by contrast, nucleic acids are linked by phosphoester bonds, being a reaction between the hydroxyl group on the phosphate and the 3' hydroxyl group on the pentose sugar. Last note about the structure here, if this R group is a hydroxide, this structure is known as NAD, whereas if the R group is a phosphate, this compound would be known as NADP. Now for the actual reaction that occurs. The redox reaction deals only with the heterocycle of the nicotinamide shown here. The hydride ion is essentially added to this carbon here, and in doing so results in the introduction of 2 electrons to the cyclic structure. This results in the rearrangement of the electrons as shown, which is fairly easy to do, so to speak, as the pi-bonded electrons in these structures are delocalized and are able to move fairly freely. The rearrangement of these electrons also shifts 2 electrons onto the positively charged nitrogen atom. This movement results in the structure shown here. This structure on the right is now of NADH, signifying that the NAD molecule now has 1 additional hydrogen atom. It may be difficult to discern where the 2 electrons and proton are now being held, so let's take a closer look at this. Here is a more detailed view of what is going on in this reaction. On top is a look at the nicotinamide structure along with the implicit hydrogen shown. The rest of the structure is abbreviated as the ribose sugar attached to the adenosine diphosphate. On the left is NAD+, as shown, the hydride ion is added to the carbon on top. This results in this carbon here being bound to two hydrogen atoms and allows the double bonds to shift away as the carbon now has a full octet without the need for a double bond. This shift in electrons then allows other electrons in double bonds to shift to the nitrogen, providing it with a lone pair and resulting in a neutral charge. We can see this in more detail here below, just as a nice visual way to see this movement of electrons. And if I zoom in a bit here, on the left again is all the electrons in the ring structure using a tedious Lewis dot structure. These structures are typically learned in early general chemistry in preparation for undertaking organic chemistry and are useful in having a good visual of all the electrons in action. On the left again is NAD+. Here I have circled all sigma bonds in green and all pi bonds in this purple color. If we count the electrons that surround the atoms in the ring structure, you'll see that there are a total of 30 electrons. When this hydride is added to the structure, it brings 2 electrons and 1 proton. Although this may not be accurate to the actual reaction mechanism, this can be thought of as follows. The 2 electrons from the hydride can be used to bind to the carbon here on top, using up those 2 electrons and the 1 proton. This essentially forms a sigma bond between the carbon atom and the hydrogen atom. This means that the carbon does not require these 2 electrons here to satisfy the octet, allowing those electrons to shift in a clockwise direction as shown here. Since these electrons are now shared between these 2 carbons, this means that the pi-bonded electrons between the nitrogen and the carbon are no longer required, as this carbon's octet is also now satisfied. This allows these 2 electrons to shift onto the nitrogen, resulting in a single bond and a lone pair. We can also check the formal charge on the nitrogen in the ring structure using the formula, the number of valence electrons minus half the number of bonding electrons plus the number of lone electrons. Nitrogen normally has 5 valence electrons, and in this case it has 8 in bonds and 0 lone electrons. Using this formula on NAD, this provides 5 minus 1/2, 8 being the number of electrons in bonds, or 5 minus 4 equals 1. This means that nitrogen has a charge of +1 in the structure of NAD+, which is where the positive charge on NAD stems from. After the reduction to NADH, the nitrogen has 6 bonded electrons and 2 lone electrons bound to it. This changes the formula to 5 minus 1/2, 6 being the number of bonded electrons, plus the additional 2 electrons that are a lone pair on the nitrogen. This of course simplifies to 5 minus 3 minus 2, or 5 minus 5, and that of course equals 0. This means that the charge is now 0 or neutral. And lastly, for completion's sake, counting the number of electrons in the ring structure results in a new total of 32, accounting for the 2 electrons that have been added from the hydride. We also have 1 additional hydrogen shown here, accounting for the proton. And importantly, these reactions are reversible, and thus oxidation or reduction of NAD+ and substrates occurs and is important in a variety of biochemical reactions.